I think people all know the orbital cycle, or they know that there is a precession which acts at about 20 kiloyears, the time cycles, and tilt, which is 41, and eccentricity, known around 100 and 400 kiloyear cycle. And this are due to the fact that Earth is going on eccentric orbital orbits, and also it has the North Pole is not centered on the perpendicular to the ecliptic. So precession, in fact, is a wobble of the Earth around its axis, and it points every 10,000 years to different stars, North Stars now, and Vega, it was 10,000 years ago also. And this has no consequence at all if we were not in an elliptical orbit. This is, because we are an elliptical orbit, the Sun is not centered on the center of the circle that make Earth around it, and it goes, and we don't notice it. We are going closer to the Sun in January, and far away from the Sun right now in June and July. And this has a strong consequence on what we call precession. In fact, right now, we are, at the winter, close to the Sun, and during the summer, far from the Sun. But 100,000 years ago, it was exactly the reverse. And this has a strong consequence on the energy received on Earth. For example, right now, in the winter, we receive 1,420 watts per square meter. In fact, in June or July, we receive a little bit less. If it's warmer right now on the northern hemisphere, is because of the tilt. But at the equator, it's a little bit colder. We don't notice it really right now, but in fact, it has strong implication when we go to the climate. And people think that orbital cycle and Milankovitch cycle are exactly the same. In fact, it's not exactly true. Milankovitch, about 100 years ago, and described the fact that the orbit could change the ice volume of the Earth. And this was, he realized that the energy received at the top of the atmosphere in high latitude had an effect on ice. And therefore, we can go from the insolation at 600 degree north in the summer, which is on the left diagrams, which is an evolutionary periodograms, and you see the yellow line, which correspond to a cycle of 23 kiloyear cycle here, 19 and 41, the tilt. And here you have the insolation record. And this, you see, there is no 100 kiloyear cycle in this. It's because, in fact, the eccentricity is just the modulation of the precession. So, in fact, when you are looking at the insolation at 65 degree north in the summer, you don't see any eccentricity. That means the 100 kiloyear cycle. But when you look at records, for example, ice volume, the 100 kiloyear cycle for the last 800,000 years is extremely important. You see the ice volume record here. It doesn't look at all like the insolation, and it is related to the fact that there is a non-linear response of the ice. The ice sheets were very large and their variation were very large in the last 800,000 years, and so they were growing very slowly and decay very rapidly. And this response of the ice produced the fact that they were not able to grow and decay at 23 kiloyear cycle. And so they jumped to the long-term response at 100,000 years, 100 kiloyear period. And before, the ice volume was not that large, and so they were responding to the 41 and before to the 20K. So in fact, the fact that we have a 100 kiloyear cycle in many paleoceanographic records for the last million years is because the ice sheets were extremely large, which was not the case before. So the 100 kiloyear cycle dominates the climate since 800,000 years, but it's also most of the paleoclimatic archives have this 100 kiloyear cycle. For example, here on the right panel, you have a record of temperature in red, sea surface temperature in the Western Pacific warm pool, the place where you could think that is the least influenced by high latitude and ice, because you are in the warmest place in the ocean. And you see that here you have the temperature of the sea surface is following the 100 kiloyear cycle because of the ice volumes, the sea level change, and also the salinity variation follows the 100 kiloyear cycles. And when you go in the 41 kiloyears realm, which is a tilt, and then you see that temperature and salinity are following the 40 kiloyear cycle. So the ice volume has extremely strong influence on the ocean and on the continent's climates. So most of the paleoclimatic archive show this. And some time ago, I produced a record. I was interested in a core located south of India, of the Maldives. And here I was looking at the percentage of Florifera profunda compared to the other Coccolithophores. And to my big surprise, here you have the record with the yellow dots, and here the same record of the same core with delta O18 in red, and percent of carbonate in blue. And you see that percent of carbonate, and especially delta O18, which represents a combination of sea level and temperature and salinity, you don't have at all the same dynamics. And what is very interesting is that the pink dots are following the yellow line, which is precession, which is in fact the insolation in low latitudes, which drives these variations. So here in red you have the periodogram, and you see that here on the right part you have the high frequency, on the low part the low frequency, and the precession here is very well marked in this record. Instead here, on the carbonate in blue and the periodogram is in yellow, you see that the precession is extremely small, and you have a strong 100 kiloyear cycle. Instead here you have 2 bits, and you have a 400, 122, 93, and a small 41. And so this is a very different. Coccolithophores plays a high pitch, and the climate, in fact, the base. And so this is why there is such a difference. This was very important for my research, and I tried to understand, and in fact the answer was given a little bit earlier than my work by Barbara Molfino and Andrew McIntyre, is the fact that Florifera profunda is living in the deep photic zone, at the limit of they are living in a place where most of the phytoplanktons are not able to grow. Instead, this phytoplanktons has the possibility to grow in low light. And because they are in the lowest part of the photic zone, they have a lot of nutrients. Instead, when you are at the surface, there is less nutrients because they are used by most of the phytoplanktons, especially that they take out most of the nutrients. And so there is when you have a lot of chlorophyll in the surface, is where, because you have an enhancement of the surface due to upwelling, for example, of nutrients at the surface, and then you have a high biomass, and Coccolithophores take benefit from it, and they survive at the surface, and they live very well. And instead, Floristera profunda has no advantage to be in this area. But when in the central gyres, central ocean gyres, where the stratification is very strong, the nutrients are limited at the surface, so the abundance of most of the phytoplankton, except Floristera profunda, which live at the depth. And so we were able to produce a transfer function for primary production using Floristera profunda, and we did that. And last year, Hernandez Almeida produced a new one, a new transfer function, which is with more core tops taken. Here it was just Indian Ocean core tops, and they produce a beautiful database of all the ocean, and the transfer function is very similar to what I produced 20 years ago. And so we can look here. The time is going to the right as modelers, is because I produced this paper some time ago with modelers, and they wanted me to put the time backward for me. So here you have 150,000 years ago and 0 here. And here you have the cycles, and you see Floristera profunda, which is going in cycles, precession cycle. And you see here the 23 kiloyear cycle is the most prominent. And here you have the delta 18, and it's very different again from this one. And it's very surprising because the core where is located north of Australia, close to the Arafura shelf. So in fact, this core here is now under the Arafura Sea, this plateau, but 10,000 years ago or 20,000 years ago, it was exonded because it was dry because of sea level, and so the coast was very close to the shore. In fact, here instead now is far away, and you see the deglaciation is here, and there is no event for the Coccolithophores. So in fact, productivity in this area was not following temperature of the sea, was not following also the fact that the sea level changed. And they were purely going through precession, which is quite striking. And so there is a kind of difference between most of the proxies of climates and phytoplankton, I will say, because it's not only the Coccolithophores, but productivity is not following the global climate. Another thing that is interesting, Jorinsia spoke about size of coccoliths, and here I compare in the same curve that I presented before the ratio between the two sizes of Gephyrochapsa, the large one and the small one, and I was producing sometimes in core tops and also in ratios, the ratio between and in the core. And I have the same results by Floristera profunda. So there is a relation between the size and the productivity, apparently, at least in the central Indian Oceans. The same thing is work. This was my first work during my PhD. I was looking at the difference between Reticulophenes, small one and large one. And here on the left, in the Miocene, I had the ratio between small and large Reticulophenes, and also it was following a 20 kiloyear cycle. And this was not always the case, because in fact, on the right, you see the record of these two cores which were located in the North Atlantic. And here is Upper Miocene, and here you are close to the Pliocene-Miocene boundary, and you see that there is a kind of a divergence in size. They are Reticulophenes at one mode, and they become bimodal in both sides, and it's in this area, in the place where it's bimodal, that I produce these two records. So there is a kind also of evolutionary trend in between these groups. So size matter. Recently, Bandif et al. Produced a paper showing that genetics is evolving in terms of recurrently they produce different, the Gephyro-capsid, Reticulophenes, but Gephyro-capsa in that case, produce a change in size every about 500,000 years. Here is Gephyro-capsa cariabenica, which produce different species that are Gephyro-capsa oceanica, to Emiliania exlehai, and Gephyro-capsa parvula. And so their genetic difference are size difference, and all the size Coccoliths Gephyro-capsa species have evolved because of their size, and they were produced by one ancestor which lived 500,000 years ago, and so they were events before and increase a little bit like Jeremy also showed that in a Reticulophenes, as I do in the previous slide I showed. So this is an important thing that I wanted to understand what was going on in the Plio-Pleistocene, and so I produced, I was not alone, on Clara Bolton and Baptiste also helped me to produce these 8 records from this area in the Central Pacific, in the Western Pacific and Eastern Indian Ocean, and we look at a lot of samples and produce a combination record of Coccolith length here, and you see from the Plio-Pleistocene boundary to the present, the size of the Gephyro-capsids in terms of Coccolith length. And you see that it goes from different cycles, and there are time of which is bimodal and time where it's not bimodal. And usually what we noticed is that the size, the average length of the Coccoliths are following the 400 kiloyear cycle, which is here. But it was difficult to understand this, to understand what was going on, because you have different species and just one record. So we tried to produce a systematic index, what we call delta mass, and which is a ratio between the difference between the large Coccolith, the mass of the large Coccolith minus the mass of the small Coccolith. For example, here the mass in this sample, the mass of Gephyro-capsa minus the mass of Gephyro-capsa ericksonii, oceanica minus ericksonii, and you have a large delta mass. And here where Gephyro-capsa cariabenica is, there is only unimodal, so the delta mass is very, very small. And if we produce the delta mass in all records, so on the 9 records, the stack is a red curve, and the data from each core is the black dots. And you see that in every record in all the area, which is quite large, but where we try to do our work, where we did our work, and they are extremely parallel. They are all the same. So we can use it because it is an evolutionary system and not ecological. This is the evolution of the Coccolithophores that is represented by the delta mass. So we can perform a spectral analysis on it, and we see that here you have the 100 kiloyear bar, 100 kiloyears, and there is no precession, no tilt. This is just eccentricity. This is different. Here is a delta weighting. I already presented this. And here you have the 100 kiloyear cycle in the delta weighting for the last 8,000 years. And here you have the 40 kiloyear cycle. Here you don't have anything here. It's very smooth. And you have a strong 100 kiloyear cycle and 400 kiloyear cycle for the last 20,000 years. And this is the record and the coherency here between insolation or precession, eccentricity in black here, and this delta mass record, and here you have a strong coherency. And as I told you before, delta O18, for example, so ice level, has only 100 kiloyear cycle in the last 800,000, and here there is only 40,000 years and nothing else. No 100 kiloyear cycle, no eccentricity. And in the ice volume, there is neither a 40 kiloyear cycle. Here you can see it, here it is. There is a 400 kiloyear cycle in this record, which is quite strong. And so this is extremely strange. Not strange, but we think that the eccentricity is driven a change in seasonality in low latitudes, and using this seasonality produce a large number of ecological niches in which when you have a large eccentricity, in that case, for example, here, at the equator, you create a seasonality which doesn't exist right now at the equator. And here you have, you produce ecological niches which are different between summer and winter, and then many species can evolve. Instead, when the eccentricity is very low, there is almost no seasonality at the equator, and therefore there is only few species. The ecological niche are limited, and this change in number of niches produce these evolution curves. And this is just the last example that I produce here. So here you have the precession with the ratio between small and large Zephyrocapsa in light blue, and you see it follows the precession here very well. Instead, the delta mass, which is evolutionary, there is almost no precession, but there is the eccentricity with the 100 kiloyear cycle, which is here. So in fact, with delta mass, we follow the evolution, which is different from ice volume, for example. And here, with the ratio between different species of Zephyrocapsa, we follow precession. So my conclusion, we have a striking feature of Coccolithophores ecology and evolution is their dynamics cannot be related to global climates, and as most paleoceanographic proxies. The reason is season. The seasons are extremely important for Coccolithophores, and this is why I think a paleoceanography of using Coccolithophores is very interesting, because we are looking at a different angle from other paleoceanographers which look at annual cycles. Their proxy are always annual. Instead, when you look at phytoplanktons, you are looking at seasonality, which behave very differently from most other proxies. And the evolution, I think, is the second part of my talk, is related to season also and eccentricity. And this is very different from the Milankovitch cycles. So this is a very different type of cycle, which could have a very strong impact on older climates, because you know that in pre-quaternary sedimentary record, also sometimes we find 100 and 400 kiloyear cycles that cannot be related to global ice volume, because the ice volume were often limited in these periods. And why do you have a 100 kiloyear cycle and 400 kiloyear cycle? This is a mystery, and maybe this is because of the production of carbonate fluxes of carbonate by Coccolithophores, which changes on these values. So evolution could influence the sedimentary record. Thank you.